Hello, I'm Dave Brown. Today we'll continue our study of solid-state electronics with Chapter 2, which is entitled Transistors and Diodes. So far, we have considered only a single p-in junction. A semiconductor device can be made which has two p-in junctions. This device is the transistor. The word transistor comes from transferring current through a resistance. Hence, transfer plus resistor results in transistor. The operation of the transistor and how amplification is achieved by transferring current through a high resistor will be covered in a later chapter. A semiconductor diode has only one p-in junction, but a transistor has two p-in junctions. The transistor may have a thin layer of N-type material sandwiched between two layers of P-type material called PNP transistors. Or it may have a thin layer of P-type material sandwiched between two layers of N-type material, in which case it's called an NPN transistor. In either case, the transistor must be correctly biased if it's to operate properly. Now let's look at a PNP transistor to see how it should be biased for proper operation. Remember, when we connected a battery to a single p-in junction, a large current flowed when we connected the positive terminal of the battery to the P-type material and the negative terminal to the N-type material. We called this forward biased. Remember that also when we connected the negative terminal of the battery to the P-type material and the positive terminal to the N-type material, very little current flowed, and we call this condition reverse biased. For a transistor to operate properly, one p-in junction must be forward biased and the other p-in junction must be reverse biased. This is accomplished by connecting two batteries to the transistor like this. For ease in discussion, we will call the two p-in junctions Junction 1 and Junction 2. When we connect the batteries like this, Junction 1 will be forward biased and Junction 2 will be reverse biased. Now let's take a look at what is happening to the current carriers or holes inside the transistor. Since Junction 1 is forward biased, holes will flow across the junction from the positive terminal of battery 1. When the holes cross the junction, they can go in either of two places. They can go out of the transistor to the negative terminal of battery 1, or they can cross Junction 2 and go into the P-type material. Some of the holes will go out of the transistor to the negative terminal of battery 1. But since they are traveling very rapidly and the layer of N-type material is very thin, most of the holes will cross Junction 2 and enter the second layer of P-type material where they will be attracted to the negative terminal of battery 2. Most of the holes will cross Junction 2 even though it is reverse biased. The current through the transistor crosses both Junction 1, which is forward biased, and Junction 2, which is reverse biased. The forward biased junction has a low resistance, and the reverse biased junction has a high resistance, and the current is almost the same through both junctions. According to Ohm's law, when the same current is flowing through a low ohm resistor and a high ohm resistor, a small voltage drop will occur across the low ohm resistor and a large voltage drop will occur across the high ohm resistor. The same principle can be applied to the current flowing through the low resistance forward biased junction and the high resistance reverse biased junction. A small voltage drop will occur across the forward biased Junction 1, and a large voltage drop will occur across reverse biased Junction 2. If the current through Junction 1 is changed, the current through junction 2 will also change. And change in current will cause a small change in the voltage drop across junction 1 and a much larger change in the voltage drop across junction 2. Now we can insert a resistor between the P terminal and battery 2. Since this resistor is in series with junction 2 and battery 2, the same current will flow through the resistor that flows through junction 2. We call this the load resistor and designate it R sub L. Any change in current through junction 2 will cause a like change in current through R sub L, and a corresponding change in voltage across R sub L will occur. This change is called amplification, and this is the way a transistor amplifies. We have explained how a transistor amplifies using a PNP transistor. The NPN transistor works the same way, except the polarity of the batteries would be reversed. The layers of the N-type and P-type material in a transistor have names. In a PNP transistor, the 3 layers are called the emitter, the base, and the collector. One layer of P-type material is the emitter, the layer of N-type material is the base, and the other layer of P-type material is the collector. Holes or positive charges are emitted from the emitter, flow through the base, and are collected by the collector. For an NPN transistor, one layer of N-type material is the emitter, the layer of P-type material is the base, and the other layer of N-type material is the collector. In an NPN transistor, electrons are emitted from the emitter, flow through the base, and are collected by the collector. Here are the transistor symbols used on schematic diagrams of electronic equipment. This is the symbol for a PNP transistor. Note the arrow pointing in proudly toward the base. This is the symbol for an NPN transistor. Note the arrow points away from the base or is not pointing in. A semiconductor diode is a p-n junction. It is made from p-type material and n-type material joined together. We can represent the diode or p-n junction like this. However, in electronics, it is better to represent the diode by a symbol. This is the symbol used for semiconductor diodes. The P side is represented by the arrow and is called the anode, or sometimes the plate. The N side is represented like this and is called the cathode. The P side is the anode, the N side is the cathode. The arrow points in the direction of easy current flow, or in the direction of conventional current flow. The early scientists and experimenters such as Benjamin Franklin and others had no way of knowing exactly what electricity was or in which direction it would flow. For sake of convenience, they chose to represent the current flow as flowing from the positive terminal of a battery to the negative terminal. Today, we know that electrons move from negative to positive, but the conventional direction established by the early scientists remains, and the arrow on the semiconductor devices such as diodes and transistors point in the direction of conventional current flow. If we return to the basic electronics for a moment, we remember that when the positive terminal of a battery is connected to the P-type material and the negative terminal to the N-type material, the diode will be forward biased and will conduct, or a large current will flow. If we reverse the battery and connect the negative terminal to the P-type material and the positive terminal to the N-type material, Very little current will flow, and we say the diode is reverse biased. An ideal diode would be like a switch, closed when it's forward biased and open when it's reverse biased. The characteristic curve, a plot of the voltage across the diode versus the current through the diode, looks like this. Ideal diodes do not exist, but many practical diodes do approach the ideal diode and can be considered as ideal diodes for many applications in electronic circuits. In the United States, most of the power we use is 110 volt, 60 hertz alternating current. By this, we mean the current alternately flows in one direction and then the other direction 60 times each second. In many foreign countries, the frequency is 50 hertz. The wave form of this AC is a sinusoidal wave, or more commonly called a sine wave. In many electronic applications, it is necessary to have a direct current, or DC, power source. Examples are the power supplies in radios, television sets, and electronic controls for industrial machines. DC can be obtained from AC by a process called rectification. The rectifier may be semiconductor diodes, selenium rectifiers, vacuum tube diodes and rectifiers, or other devices. We will look at the semiconductor diode to see how it changes the alternating current, or AC, into direct current, or DC. The other types of rectifiers work very similarly. Let's look at the AC sine wave. The voltage begins at 0 and then increases to a maximum voltage, after which it decreases to 0 again and then begins to go negative until a maximum negative voltage is reached, from which point it returns to 0 volts again. For our common 60 hertz AC, this is repeated 60 times each second. If we apply this AC sine wave to a p-n junction, or diode, the diode will be forward biased during the time the sine wave is positive and reverse biased during the time the sine wave is negative. So the diode will conduct during the time it is forward biased and will not conduct during the time it is reverse biased. We can observe the diode is conducting and not conducting by building this simple circuit and observing the voltage across the resistor on an oscilloscope. For safety, in order to reduce the chances of getting an electrical shock, let's include a low voltage transformer, such as a doorbell transformer, in the circuit. The input voltage will look like this, and the output like this. The diode conducts, or current flows, during the positive half cycle. In other words, the diode acts like a closed switch. During the negative half cycle, the diode is reverse biased and does not conduct. In other words, it acts like a switch in the open position. This is called a half-wave rectifier. The output of a half-wave rectifier will not be a steady DC, but rather a pulsating DC. The pulses will occur 60 times a second, the same as the power line frequency. In many foreign countries, the frequency is 50 times a second. A power supply using a half-wave rectifier will provide DC to operate electronic circuits. Most AC-DC radios use half-wave rectifiers to provide the required DC. There are also full-wave rectifiers. Those will be covered in the next program. This concludes Chapter 2. I'm Dave Brown for Teletrain.